to like, okay, that's okay. Okay, so I'm very happy to have Ting here. So she is an assistant professor at the Department of Astronomy and Astrophysics, associate faculty member of the Dunlap Institute at the University of Toronto. Also, she did her PhD. Well, you do your undergraduate students all over the world because you were an Erasmus. So she was in Germany and a lot of places. She was working also she did her PhD at the Texas A&M University. I think under the supervision of Jennifer Marshall. Mm-hmm. Yeah. So and she got like a NASA Hubble Fellowship Program Einstein Fellow at the Carnegie Observatory, and also she had a joint appointment in the Department of Astrophysics Science in the Princeton University at the Carnegie Princeton. As a Carnegie Princeton Fellow. So, and after that, she got the assistant astronomer position at the University of Toronto. So she is a very good researcher in the field of the cosmology about the understanding the Milky Way, and she has a lot of leadership in studying the stellar streams in the Milky Way, and she will talk about that today. So thank you, Will. So proceed with your talk.
Thank you. Thanks, Clara, for a very nice introduction. And I'm so happy to be here. Actually, I got here early this week and I was attending the Science Advisory Committee meeting for CFHT. And then I'm actually going to be here next week for the DESI collaboration meeting. Also in the west part of the big island. So I find, oh, Friday is free and what I should do, and contacted Clara, or somehow Clara know I'm coming. So that's why I'm here today, and I'm very excited that it's my first time to be in Gemini North. So I'm very glad to be here. And yeah, I want to take this opportunity to talk about some of my research. So I've been doing, as what Clara mentioned, I do a lot of things. We call it cosmology or near-field cosmology, but it really is like stellar population related science. I to study the Milky Way and nearby galaxies. And particularly today, I'm going to focus on one type of, I would say, tracers that we're using them to study the Milky Way. These are the stellar streams that I will explain later. So I will mostly focusing on two collaboration or like two type of group of work that one is from S5 that I'll mention later, and one is another one called the DESI, the Dark Energy Spectroscopic Instrument. I'll also mention very briefly at the end of my talk. So I'll start with the simulation of dark matter. So this is dark matter simulation, a zoom-in simulation centered around a Milky Way-like analog. So there is the main dark matter halo, like our Milky Way, the visible matter is kind of centered on this. And there are also a lot of dark matter subhalos that what we call like the clumps orbiting around our Milky Way, the main halo. Some of these big clump, slightly bigger clump, it's too smaller than the main halo, will form stars and form this galaxy there. So one of the very well-known galaxy orbiting around our Milky Way is a large Magellan cloud. So this is in the northern hemisphere, but if you ever have a chance to go to Gemini South or anywhere in the southern hemisphere, you will see these blobs of clouds on the sky. These are the satellite galaxies of our Milky Way. So here, these are the two large and the small Magellan cloud that you can see with your naked eye. So there is dozens of these satellite galaxies orbiting around our Milky Way. There's also these much more dense global clusters that you probably all know that's orbiting around the Milky Way. And these galaxies, all global clusters, so will some of them, when they get very close to the Milky Way center, because of the tides, they will get tidally disrupted and then forming these linear structures, that ribbon-like linear structures on the sky. And so the disrupted galaxies, disrupted star clusters, before they fully mixed with the Milky Way halo, we will see them as a structure of streams because they are like rivers on the sky. Sorry, the movie is a bit lagging. And that's where this stellar stream that we have been seeing, and they are trying to use them to study the formation of the Milky Way and also the nature of dark matter. So here I'm going to first introduce the different science that we think can do with stellar streams. And I'm going to show these from 3 different aspects by pointing a few questions we'd like to answer in different variety of science field. So the first part is on the formation of the Milky Way stellar halo. So the question here we could ask are something like, what are the building blocks of Milky Way stellar halo? What do the most metal pool star coming from? Like we know that the galaxy forms hierarchically from smaller galaxies to larger galaxies. And our Milky Way halo, although it's just a small fraction of the stars compared to the entire galaxy, but it's good to understand how the halo was formed and where the most metal pool stars in the halo come from. The second part that what I think stellar streams are powerful to study are connected with the mass and potential of the Milky Way. It is important to understand precisely what the mass of the Milky Way is, especially we're doing a lot of observation compared with simulation. And we want to put our Milky Way into a cosmological context that we wanted to know when we compare with the Milky Way analogs in the simulation, what is the mass we should really compare with. So the Milky Way's very mass at 0.8 or 1.6 time 10 to the 12th solar mass. We still don't know it very well by a factor of 2-ish. So the plot here you see is a review paper done by Wen-Ting showing that with different methods, different tracer, that with different color here, there is at least a factor of 2 difference by constraining the mass of the Milky Way. Of course, it's not just only the mass is important, the shape of the potential, the Milky Way potential profile, whether it's triaxial or spherical, is also important to understand. And that's what we think that stream can help us to study. The last one that I think stellar stream are very sensitive or very unique about is to study something related to things we call dark matter subhalo mass function. So different dark matter model, for example, the cold dark matter, what you see here on the left of the third column here, and warm dark matter, that they give very different predictions for the number of dark matter subhalos. And the cold dark matter will predict way more dark matter subhalos than the warm dark matter, which we all know about that. However, we also learned that not all of these dark matter subhalo will have enough mass to kind of attract enough gas to trigger star formation. So a lot of these dark matter subhalo will be dark and not form galaxies. So we have been using counting the number of galaxies or measure the satellite luminosity function in our Milky Way and other galaxies to study the dark matter subhalo mass function to infer whether dark matter is cold or warm. But there is a threshold down to something around the 10 to the 8 solar mass. Dark matter subhalo doesn't have star formation triggered. We cannot really identify them as galaxy anymore. So what we think that a possibility is to use streams to constrain and find these dark matter subhalos at 10 to the 7 solar mass or lower. And the way is the following. It's complete dark. It doesn't have any gas. It doesn't have any star there. But if these dark matter subhalo kind of passing by a stream, so this is a stream, and you will see that the way to think about is the stream is moving on the sky. But if there are a dark matter subhalo passing by, the stars, because of the gravity, will kind of attract to each other where the paths happen or the encounter happen, and then keep moving forward, and then leaving these kind of density gaps or variation in these streams. So we think that we won't be able to see these dark matter subhalo, but the density variation in the stream may be able to tell us something about finding these dark matter subhalos. It infers the size of the dark matter subhalo, infers the mass of the dark matter subhalo. So we're trying to find these kind of signatures or structures. A very well-known one has been recently seen. It has been known for a while or speculated for a while, but the first time with very strong evidence from the Gaia release after the Gaia DR2 is this GD1 stream. What you're seeing on the top is the real data coming from proper motion from Gaia and parallax also from Gaia, and then photometry from Pan-STAR, a Northern Hemisphere imaging survey. And all of these black dots, what you're seeing here, are member stars belonging to this stream. So you can see that in addition to just the stream that people have been noticed, there is also this spur kind of feature that we are confident these are stars that are part of this stream. But this cannot be explained without without a full understanding like where it's coming from. And Abanasa et al. In 2019, they tried to model the stream using some perturbations, like some kind of perturbers to perturb the stream, and they can mimic this spur and a gap feature with some perturbation. We don't know what it is, but with time of the perturbation, when did it happen? It's about half giga years ago, with the mass around something like 10 to the 6 solar mass, with a size about 10 parsec, very compact, and the minimal, the impact parameter is something around 15 parsec at a speed about 250 kilometers per second. So that's what the best fit model looks like based on the data here. If you look at the size of the perturber and the mass of the perturber, this shaded region shows where the perturbation, the best fit perturber looks like. So it's very compact and with a mass around 10 to the 6, 10 to the 7. If you believe that these perturbers are from lambda CDM predicted dark matter subhalo, this is where the shaded region, the other shaded region predicted should be. So it is actually much more compact than a dark matter subhalo based on the CDM model. So this is interesting. It is first saying we need something to make this happen. On the other hand, it seems doesn't fit with the current dark matter theory. So is it really coming from a compact perturber? At the same year, another group, De Broglie et al., showed that the spur could be caused by interaction with Sagittarius dwarf galaxy, although it's a very low chance that these happen based on the current orbit of Sagittarius dwarf galaxy, but it's not impossible. So this is just one stream giving one kind of example showing these kind of features. And it's very important to find more of these kind of things in the future to understand whether or not we can explain that there are these dark matter subhalos below the star formation threshold. Okay, so this is 3 different topics of what I think the stream can help us to answer, starting from the formation of the Milky Way stellar halo to the nature of dark matter. And so the streams are very cool to do the science. And of course, we need to find these things first. So this is a view from Stone Digital Sky Survey in the northern patch of the sky, part of the northern sky. So you can see the Sagittarius stream here, which is the first one discovered 29 years ago. So next year will be the 30th anniversary of the first discovery, the discovery of first stellar stream. This is originated from a dwarf galaxy, Sagittarius dwarf galaxy. There's also Palma 5 stream, which is a global cluster Palma 5 with the tidal tails. We still can see the global cluster in the center here. There's also GD1 stream. It is progenitor free, so we don't see a progenitor of a global cluster anymore, but we think it's coming from a global cluster, like what I showed in my previous slide. There's also this stream called Orphan stream. Its name coming from, it's a first dwarf galaxy stream, but do not have a dwarf galaxy progenitor scene. That's where the Orphan name comes from. And then, so the way how these streams are found in the image survey era was mostly doing this, what we call match filter scanning algorithm. So you have a metal pool isochrone and you scan through in distance. And this is where a global cluster is at a particular distance around something 15 kiloparsec. And then you scanning through, you will see this over density. So on the right, what you're seeing is number of stars in each pixel, just by counting the stars that fall in that isochrone filter. And you can see the number of stars get more at a particular distance when it's at the distance of the global cluster, and it pops up and then disappear when we move further. So this is something led by Nora Shipp, who was a graduate student at the University of Chicago when she led this work. So at that time, I'm part of the imaging survey in the Southern Hemisphere using this dark energy camera for the dark energy space, which Clara is also part of it. So we did Nora led this, but we're scanning like basically distance between about 10 kiloparsec to 50 kiloparsec using this match filter algorithm. And you can see, right, the black here is over density, or say higher number of stars in each pixel. The white is less number of stars, a fewer number of stars in each pixel. And you can see that at particular distances, you see this kind of linear ribbon structure pops up. And that's all the streams that we have identified in this southern galactic caps. This is the South Pole, the southern galactic pole, and this is the over densities we are seeing, or the stellar streams we are seeing in several in this data set. So if we this is the same plot, the same footprint as the previous one of the southern sky, but making it a color map like what we did here for the northern sky. The idea is just to take the density map at different distances in different colors. So the blue is for a closer distance, a 10 to 15 kiloparsec, and then the green is 15 to 25 kiloparsec, and the red is a bit more distant. And then each distance you have a density map, and then you have one color, and then you can make an RGB map. And so you can see like these structures basically outskirt of LMC, and that's very distant. And here some of the stream, like this is Sagittarius stream, it's kind of in the intermediate kind of distance. So this is how you can see all these colorful structures like in RGB deposit map. Of course, this is how we have been finding streams using the deep imaging survey, like Sloan Digital Sky Survey in the Northern Hemisphere and the Dark Energy Survey in the Southern Hemisphere. And the Gaia DR2 and then later DR3 release made us to able to find all these, especially the nearby streams at the range about something within 10 kiloparsec. It's revolutionary finding all these streams. Now that's what we know about Milky Way stream has maybe over 100 of those. And these are by finding not only that in the color magnitude space, like what we did with the deep imaging, but also have the proper motion information that knowing all these stars are coherently moving on the sky following a potential for Milky Way. So there's dozens of them finding. So when I started working on this with my collaborators, finding some of those in the dark energy survey, I tried to count how many of the stream has been known by then. So I was doing this cumulative number of stream discovery as a function of the year it was discovered. So again, before 2000, the only one we know is a Sagittarius stream that from that Sagittarius dwarf galaxy. And down the late in 2018, the reported there's about 65 to 70 stream known. And I didn't even count further after 2018 because the past 5 years, I figured out there's no way to count it. But that was 2018, I found, oh, there are so many streams that's been discovered with a variety of methods, but they hardly had any spectroscopic follow-up effort to confirm these streams are real or not, to study these streams, to kind of answer the question, scientific question we are interested in. So that's what I spent on and I worked on. And I want to just highlight why it's really not possible to kind of figure out how many streams that we have now. So this is a paper published early this year using a machine learning method that in this paper they published there are 90 new streams. They claim there are 90 new streams in their algorithm detection, but they don't release any catalogs or anything. So there's no way we can really confirm how many of those are real, whether or not there's an overlapping. But this is like the number of streams. I think all of these was just this year or in the past year and a half. So the number of streams in our Milky Way will really explode, I think, exponentially. Okay, so that's where I was at in 2018. I was a postdoc and a part of the team who discovered all these streams. I feel like, oh, I know at least for these streams, I know where they are on the sky. I know what the distance they are. I know how to best select the target. So let's follow up these streams. So that's what I wanted to do. And that's where I started this collaboration called the Southern Stellar Stream Spectroscope Survey, that with a group of people from the Dark Energy Survey who led the work to do all of the stream discovery, and also another group of people from Australia, because we find that the best instrument to do this is using the Anglo-Australia Telescope, AAT, because of the larger field of view, and then a few other experts in this field, and we have this team. So including Clara, that doing a lot of outlier work for the group. We have been running this for the past 5 years, and I'm going to show you guys a bit of the result from this collaboration. It's not a gigantic group, but I think it's very, very fortunate that we had a lot of great colleagues and having a very nice result. So a very quick overview about S5, the Southern Stellar Stream Spectroscopic Survey. It's originated from following up the stream discovered in the Dark Energy Survey, or DES. In 2018, and very good timing is Gaia DR2 came out with a lot of proper motion information. So we can use, at least at time, the best photometry information we have together with the proper motion information, astrometry information with Gaia to do a very efficient target selection. And what we did is, using this 3.9 meter telescope in Australia, AET. The uniqueness of it is it has a 2-degree field of view fiber positioner with 400 fibers. So instead of observe one star at a time, we can observe 400 targets at the same time with one exposure. And the fibers goes to a spectrograph with a blue arm and a red arm in instrument room. And so we can very efficiently observe these streams, because think about, right, these are stars originally from one globular cluster or one dwarf galaxy, but spread out to dozens of degrees on the sky. So really we need a wide field capability, and that's what AET is good at, even it's only a 4 meter. And for the member star that we confirmed from the AET, we feed them to a larger telescope with a shell spectrograph, so doing one target at a time, and to measure the chemical composition of the star and to understand them. And this is work that is led by Alex G at the University of Chicago to do all of the chemical abundance study of the streams. So we had a basic low to medium res to the kinematics and velocity, and then the brightest star we do chemistry study. So there's a bunch of paper we published. You are more than welcome to check out on our website if you saw any of the result I'm going to show next is interesting to you. So this is done 2022, so about a year ago, where we were at with about 12 streams that we have followed up and identified all the member stars. So here you are seeing is a Gaia map with individual member stars we identified from a variety of streams, and that's what we have been getting. And so I'm going to talk about some of these streams in my next few slides and showing you how we use the result here to answer some of these questions. And I'm going to go again, one example for each of these. So the first one is on the formation of the Milky Way's stellar halo. And as I mentioned, we want to know about the building blocks of the Milky Way stellar halo. That's something we're trying to study. So here I want to highlight one result coming from this work from S5 is a particular stream that called a Phoenix stream. So this is work done about a few years ago using the AET data. So what we did is we follow up individual member star candidates in this stream and then try to measure the velocity of the stars. What you're seeing here in cyan shows you the member stars that we identified and their velocity. So all of these stars at a velocity around something like -2.7. And based on the measurement uncertainty and the spread here, we conclude that the spread can entirely explained by the measurement uncertainty. So the velocity, intrinsic velocity scatter is almost 0 for these systems. So we think it's originally coming from a globular cluster because it has no velocity spread. And then we also compare with all the known intact globular cluster in our Milky Way. And this is a histogram showing the distribution of the velocity of the known Milky Way globular cluster. So it's very interesting that it is a disrupted globular cluster, but it has a velocity that lower than any of the known globular cluster to date. So that I think very interesting. Maybe it's telling us there used to be a lot of this metal poor globular cluster exist, but they couldn't survive the Hubble time and they disrupted. In that time, we say this is the most metal poor globular cluster stream at that time. When you say something most, it never lasts. So you probably all know this is something related to the Gemini work that 2 years later, there was another even more exciting work that led by the Pristine team and then followed up actually with Grace that a lot of people probably worked on here, that finding another stream, although at that one probably was only 5 stars. So I think we have a bit more, but still this is half a dex, much more metal pool. But this is also very astonishing, right? It's probing these disrupted remnant of globular clusters and finding more and more metal pool systems. So I think that's very exciting. And that may be connected with some of the metal pool star, EMP stars, extreme metal pool stars in our halo and how they come from. Okay, the second part I want to talk about is on the mass profile, the Milky Way mass. If you remember, that's what my middle panel is about. So yeah, about this part. And here what we find through a lot of the study that we find on these streams is we remember at the very beginning, I mentioned this, the biggest satellite galaxy of our Milky Way is the Large Magellan Cloud. So it is one of the satellite and it's coming in. Recently, we know that it come in either on its first or second passage. And the mass of the LMC is non-negligible. It's actually perturbing our Milky Way heavily, and our Milky Way is not in a dynamical equilibrium. So what we find is if we wanted to well understand the mass profile and the mass of the Milky Way, we have to also understand the Milky Way's biggest satellite, Large Magellan Cloud. So what we find of the stream, because the stars are all coming for a given stream, the stars, the debris are all coming from one system originally. And so we can use that to constrain the Milky Way mass and the Large Magellan Cloud, the biggest satellite mass at the same time. And that's what I've been doing. So I'm gonna show you, yeah, so this is the biggest satellite galaxy of our Milky Way. And so we really wanted to, if we want to measure the Milky Way mass, well, we really need to also understand the mass of the Large Magellan Cloud and its past trajectory very well. So here we're going to use all of the stream, hopefully eventually, but here I'm going to just show you one example using one of these longest one in our data set. This is actually the Orphan stream. It was originally discovered, but then there's another part of the stream discovered later called the Shinab, and then later people find it's one stream. So there's a name called Orphan Shinab or OC stream for this particular one. So for this particular stream, we have the data in all 6D. So this is what you're seeing just by rotating this stream clockwise 60 degrees. So we'll be along the stream, what we call phi 1, perpendicular to the stream, we call phi 2. And what you see here is phi 1 and phi 2 in the top panel. And then you have the distance to us along the stream. We have proper motion in the 2 dimension, again, along the stream, perpendicular to the stream, and finally line of sight velocity. So we have 5 panel here for the 6 dimension. For all these, for this particular stream, we have a very detailed data set, a very, very good data set for all the 460. These are with the individual member stars here, we were able to constrain the track. So we're showing in red. So red is the data that we observed from these stars for 60. And then we try to model this stream to measure the potential of the Milky Way, the potential of the LMC, the past trajectory of the LMC. There's a bunch of parameters there, and it was the most led by this analysis work, most led by Dennis Oker, the second author on this paper. And what you're gonna see is a movie that to fit the red points here, which is the data, and what is the model, best fit model over the past 2 gigayear. So the sign points here are the sprayed model particle, like assuming a galaxy have particles leave the galaxy form tidal tails, and finally at redshift 0 that it matches with data. So I'm going to show this movie again, and I want you to notice a few things. First is the position of this black dot, which is trying to mimic the LMC. The second is this huge kink that happened, and also this kind of motion. These vectors here showing you individual star in that project plane, what is a motion. So you can see this part is totally perturbed by the LMC passing by and then cause this misalignment. I'm going to show the movie again. So again, the past 2 gigayears, the stream gets formed and get longer, and then in the past, and then the LMC is coming into our Milky Way and get closer and closer. In the past half gigayear, the LMC get a very close encounter with the stream and perturbs the second half of the stream here. And then so the stars, if there's no perturbation, should be moving along the stream, but because of the perturbation, it is kind of going perpendicular to the stream and make this prediction of a huge kink here, because our data only stops here. But if it's correct, it says there should be something like that. So we actually put in another proposal to follow up this part, and we find something here. We don't see stream particles in this part, which naturally would be if there's no perturbation. We actually find stars here that currently will follow up. And this is show you how awesome this is. We are fitting not only the mass and mass profile of the Milky Way, but also the mass and mass profile of LMC, and also the mass, the trajectory, the orbit of LMC in the past 2 gigayears here. And this is another view of the same thing, but now in 3D. So what you're seeing again, the red is data that we collected, and the blue here are the best fit model. And now you're seeing in a 3D view that again, the stream form. This is often Schnapp stream. And then in the last half gig a year, you will see the LMC comes in and then perturb the bottom half of the stream. If there's no LMC, the stream should on this dashed black line. That's where the orbital plane of the stream. Because of large perturbation from the LMC, you can see the stream deviate from its own orbital plane heavily and form these kind of interesting structure. So that's very nice that we use one stream, we can do all of those work, but also it's not very easy to do this. And the dream in the future is to do all these dozens of streams that we have got simultaneously, and hopefully we can fit that. It's definitely challenging, but it's something that we can consider. So this is one of the results. We can constrain the mass profile in the orbit of LMC. So what we did is a few parameters to set to about the mass and the size of the LMC and give an arbitrary truncation radius because we don't know how big the dark matter halo is in the LMC. And we let an arbitrary truncation radius. And we find that within 1 sigma, the truncation radius has to be above 100 kiloparsec, and with 2 sigma, it should be at least bigger than 70 or 60 kiloparsec from the center of the LMC. So this is saying, right, although we only see like about 10 kiloparsec of its luminous part, the dark matter halo for the LMC has to extend 5 times or 10 times larger. That's the dark matter halo. We can also constrain the orbit of LMC. So if we just take the current best knowledge about the Milky Way, the Macmillan potential, and the current 60 of the LMC at the redshift 0, you will want an orbit that's in red. And our best fit show that the LMC trajectory is slightly different from what the previous know, and has also much a tighter constraint here. So that's what we think of the best orbit for LMC in the past half gig a year here. Okay, so this is the second part where I think that what stream can do in terms of constrain and measure the mass of the Milky Way and the LMC. And the third part is we said the connection with to understand the nature of dark matter by measuring the dark matter subhalo mass function. And here, you remember we talked about this GD1 stream that we see this spur and a kink feature. And here, I'm gonna show one example that we see from our data on a different stream. So this is a broken stream, probably perturbed by dark matter subhalo. So I should have changed this. Sorry, let me go back. I always wanted to do this, but I always forget. So let me just do it in real time. So I don't need to go back to a lot of slides. Okay, so I talked about this earlier about the stream we find in the dark energy survey. And I think everyone will say, oh, so cool. And the first stream they will identify is this one, and hope that catches you as well. It's not a stream actually we find in dark energy survey. It was defined 10 years before our discovery, or 5 years before our discovery, called Atlas stream from Atlas survey. But we did find another stream that just next to it, this is this one called Alika-Uma stream. That was the first discovery in the dark energy survey. So at that time, we think these two are two streams because you can see, right? It's not connected. There's a slightly different angle. And also this part of the stream come out first at the closer, and this part come out a little bit behind. So at that time, we think these are two different streams. We report them as two individual streams. But then we follow up, again, we rotate this whole stream just 30 degrees, so it's aligned. That's how we do everything. Is align the stream is called a phi1, perpendicular to the stream is phi2, but it's just a rotation you can think of for transformation. So this is the Atlas stream that I mentioned earlier, and this is Alika-Uma stream we find in DES. So for S5, we can find individual stars belonging to the stream, to the stream. So these are all the member stars belong these two streams. And what you're seeing on the right here are individual stars on the sky and in velocity in proper motion space. So to our big surprise, when we find these two streams, although they are not connected or they have some kind of discontinuity on their sky distribution, but if you look at their velocity, their proper motion, they're seamlessly connected. So we think they are just one stream. The chance of this happen to be a group in 4 and then have identical kinematics, it's not 0, but I think it's very low. So what we think it's one end of the metallicity, the chemistry, it's all the same. So we think this is one stream, but somehow there is this kink broadening feature, which is very similar to this spur gap feature that we see in GD1. But the difference here, I think it's also harder to identify this, is GD1 is around something 8 to 10 kiloparsec from us. So these features are seen without any spectroscope follow-up. Basic just need Gaia proper motion, you get all the main sequence stars, and then you will be able to naturally see these. While here, we are only getting the giant stars because this one is 3 times further. So this one is about 30 kiloparsec from us. So it's much further. So we won't be able to see it until we identify individual members and we see these kind of features. So this stream is 3 times further in the Milky Way halo, but we see something very interesting that's similar to GD1. Very coincidentally, we also find that there is a impossible, how do you say, there is a 2% of chance that this might caused by the Sagittarius dwarf galaxy, although we are still investigating that possibility. But there's also possible that it's caused by some dark matter subhalo. But this is showing you another example. We are seeing a lot of these streams in our Milky Way, and every stream that you go look into it, there's some weirdness there. Like this one is another broken stream that we see. Okay, so that gives you a picture about the S5 stream component, which is the main science goal for the survey. So we are using this AAT to do the observations. As I mentioned earlier, for all the member stars, we confirmed if it's bright enough, we will feed into the Eshel spectrograph to study the chemistry. I also have a lot of slides on that, but because of time, I don't have time to talk about that. If there's interest on the chemistry part of the streams, I highlight you to invite Alex G to come here give a talk. That's all I always say. So he's definitely the best person.
He heard you because he's there.
Oh, he's there. Okay. I'm not saying that because he's there. I always tell people to hear because he can do way better. I try to include some of the slides and then I got question I cannot answer. So I decided just let him to talk about that if you're interested. But I do want to use a little bit of time to say some anomalies program we put in S5 using the AAT. So in the past, stream is so hard to do that you need hundreds of fibers to observe a given field. But because of thanks to Gaia, we were able to do a lot of efficient target selection, remove a lot of targets that are not consistent in the proper motion, we can throw them away. So we realized when we started the survey, originally thought all the 400 fibers need to be targeting stream candidates. But we actually only need about a third of them, or maximum half of those fibers to do stream survey. So we said, okay, we can do some other science, maybe with spare fiber. Let's think about that. So it came up with 2 ancillary programs. One is on the halo survey, because that's also something I'm interested in. And then we also did a low Z survey, which is a low redshift galaxy. So it's like LMC analogs, but in redshift of like 0.05 or lower. So we have been using spare fibers to targeting these 2 different things. The halo survey is mainly actually for distant stars in the Milky Way halo to study the structure of the Milky Way. But to everyone's surprise, the biggest science result coming from S5 has nothing to do with stream, nothing to do with the halo, but come out with this hypervelocity star. And I love to talk about it, especially when I go to a university, tell students that when you study A, it doesn't really necessary to find the most fascinating result from your group is about that. It's sometimes about something else, which is the beauty of science or doing science. So this is a star that we observed as part of the S5 halo survey. And we find this star, we call it S5 HVS1. It's a hypervelocity star that we find using the spare fiber program. And the star has a total 3D velocity about 1700 kilometers per second. So let me give a little bit background about what hypervelocity star is, or the theory, what we think it is. It was proposed by Jack Hill in 1988. That time, we don't really know there is a supermassive black hole in the center of the Milky Way. I mean, we have speculation that's possible to think, but again, it's 40 years ago. I can do the math. You can do the math, like how many years ago. And so Jack Hill predicted if there is a supermassive black hole in the center of the Milky Way, if a binary comes in, one will get captured and one will get ejected super fast. And I use the analog actually coming from Dennis Overby when he wrote the article in New York Times. He says like when you're dancing with your partner, and your dancing partner get captured by another person, you will get swing out. It's like the feeling. So one of the binary star will get ejected out. And that time, Jack Hill said, if the Milky Way center has supermassive black hole, then it has to have these kind of stars ejected at speed of more than 1,000 kilometers per second. And that prediction made a long time ago, and people has been chasing to finding these hypervelocity stars for decades, started in about late 90s, early 2000. And this one, as we didn't purposely targeting it, but we did target all of the blue stars in our in the Milky Way because we are interested in to use them for halo science. And this one, hypervelocity S5HVS1, we find has ejection speed over 1,700 kilometers per second. And there are quite a few known hypervelocity stars to the community, reported by different people in the past decade or 15 years, now almost two decades, when the first hypervelocity star has been discovered. All of those has ejection speed below 1,000. So it's very interesting. It's either telling us none of these actually are hypervelocity star. Maybe they are because they have large uncertainty whether or not they're coming from the center, or maybe there are some kind of different ejection mechanism that's showing the variety of the ejection speed. Some are at 6 to 800, around 800 kilometers per second, while the one we saw is at 1,700 kilometers per second. And so this is like one of the stars that we didn't prepare for, but it turned out to be the first science result coming from our collaboration. Okay, so I don't have time to go through all of those, but I do want to highlight that we are not only starting one stream at a time. For the first time, we have, and you can see originally we did the stream with the DES footprint. This tank shape is the dark energy survey footprint. But then we realized that we can do more than just the DES footprint. We can do everything in the southern hemisphere that AET can reach. So we call these southern stellar stream spectroscope survey. So this is the release of the 12 progenitor free stellar stream with a distance range between 10 to 50 kiloparsec that observed in the first 3 years of our program. The data has been keep going, and we are still collecting data as of last month. Depending on AET continue work or not, I think our program will continue, but it's also a pretty old instrument. So we hope it can work functioning for a longer time so we can collect more data. But we have been also using like a dozen of streams to study the properties, the populations of streams as a sample and then compare with simulation. So there's a lot of result on that too for the people who are interested. I won't have time to go through all of those. But yeah, this is what we have from S5, which is a survey I led in the past 5 years, and I think it's getting very good result. But I think if this is the current or past, the next thing I'm going to show is really where I see the future is going. So right now I'm actually spending more of my time on DESI, which is actually the reason I'm here next week, that there is a DESI collaboration meeting at what's it called, Waikoloa, yeah, and they're putting a resort, so I'm gonna go see how fancy it would be later. I have no idea. I heard it's a very nice resort, but I'm not. But anyway, so that's where I'm spending a lot of time on. So in DESI, there is the Milky Way survey. I'm one of the co-chair together with Leandro, Bernardo, and Silva in University of Arizona, and this is called DESI, right? It's for dark energy cosmology. So it's not really for Milky Way, but I will show you and convince you it is definitely producing a lot of great results that will make us very busy for the next decade. So a very quick nutshell, and I think a lot of people here probably have heard it through your colleagues at NOAA Lab. So DESI is on the 4-meter Mayo telescope at peak. It has 6 lens wide field correctors with 5,000 robot fibers. So like the S5 I did with 400 fibers, and this is 5,000. So it's 10 times more than 10 times more fibers with 3-channel spectrograph. So they can observe 5,000 targets at the same time. It had the commissioning in December 2020 during the pandemic. I spent a lot of time on the mountain to help commissioning team to commission it. And then the science verification, all of the commission and science verification data is public that you can access to either in the Spectra mode or in the catalog mode on the NOAA Lab and the DESI release website, and for all the data collected by the end of May 2021. And the 5-year survey started in May 2021. So we actually, I should have another line. The year 2 has finished now, and we are currently in the course of the year 3 survey. And this is how the focal plane looks like with 5,000 fiber positioner. And this is the view of the fiber view camera to see the 5,000 fibers. And here is the spectral resolution of the spectrograph. So this is one of them with 3 channels, the blue, red, and infrared, and the 10 of them sitting at Cape peak. So it starts from about 2,000 in the blue and then 5,000 in the red. And what's powerful of it is very high throughput in almost all wavelengths, that around 35-ish percent in the blue and 50% in the red. And as a comparison, a lot of, I don't know what is the GMOS, maybe someone can tell me, but I know that a lot of the multi-object spectrograph I have used with the throughput is around 10 to 20%. So something at 30 to 50% throughput. This is every single photon comes in, right? 50% of them will actually become your data. A lot of non-astronomers think this is not a lot, but going through so many optics and all of the things actually is pretty impressive. And that's, I think, make DESI super unique. So for the Milky Way survey, it is a bright time survey. And the dark time all goes to cosmology, galaxies. We don't have any of right to choose the strategy or anything. The bright time survey first goes to the bright galaxy survey, and then whatever the left fiber goes to the Milky Way. We don't have any choice to define the survey strategy as of for DESI 1. Next week is my job here is how to argue to make that Milky Way to be a key leader for DESI 2, and then we'll see what that happens. However, although we have no choice about a strategy, no choice of where we put our target at, I still think it is very impressive and very powerful, because at each effective exposure time of 180 seconds, it does what a 2 hour does for the S5 survey in AAT. It's a 4-meter telescope. This is also a 4-meter telescope. But the 3 minutes, what we do here is 2 hour or 3 hour of efficiency on AAT, what I was doing there. However, I do want to emphasize the effective exposure time. It means like it's a perfect dark night with great seeing. So that's the way how they schedule. So for the bright time, that's the 3 minutes is around something like 1,000 seconds. That's what a nominal, the bright time survey does. But still, right, a 10 minutes exposure, no, 15 minutes exposure that does in the bright time does about the same as a 2 hour exposure on the other telescope that I am currently using great result, but I think this will be even better. The goal is to get 7 million stars between 16 to 19th magnitude, which is the same what S5 has been doing in terms of string target between that magnitude range, but with 2 hour to 3 hour exposure time per field. And this is the histogram of the first year data that we have more than 4 million stars with velocity uncertainty less than 10 kilometers per second. And you can see most of our target is between 16 to 19th magnitude. And just to give you another example, we don't usually get a lot of dark time, but we could have some of those luxury during the commissioning time when we had some just hour targeting. This is on a dwarf galaxy, which is also something I study a lot. This is called the Draco dwarf galaxy. What you're seeing here is a field of view of the one pointing for DESI. Each of the point here is a star, a target we observed. And what you're seeing in the black point, as a blue points here are what's from the Walker et al. So it's a literature that studied Draco dwarf galaxy with that find 500 members. And for DESI, we got a chance to observe 45 minutes with just one pointing. And because of the fiber collision, we could only get 200 members in that 45 minutes, but the velocity uncertainty is pretty comparable, or also a little bit lower. And we will be able to get about half, or say a third of what Walker et al. Got in 2015 with MMT. But this is what they need to do MMT observation. So what you're seeing here is just a list of masks that they took with MMT hecto shell spectrograph and exposure time here. If you add up all of the time, this is 60 hours on a 6.5 meter telescope to get 500 members. And we spend 45 minutes for 200 stars. And that's what we are at with DESI. So I think DESI is designed for wide field, but there's a lot of potential to do a lot of science in our Milky Way on streams and on dwarf galaxies, and be more efficient than a lot of big telescopes. Okay, I need to wrap up soon. I just want to highlight that the Milky Way, again, is the small group in this cosmology survey, but it has a lot of science goals that interest me, including a lot of them are very similar to what I mentioned earlier, that we try to study the shape and mass of the Milky Way dark matter halo. We want to also study the small scale substructure, like the perturbations that we see in the streams. We want to study the assembly history of the Milky Way halo and also the thick disk. And we finally want to study the metal pool stars in our Milky Way and trying to find some of those. We have a lot of results on stream as well, but I feel like because on variety of science, but I wanted to emphasize a little bit related to stream and also kind of showing you the potential of DESI. So this is a work led by Arjun Day at NOAA Lab. So at the commissioning, we got a chance to observe the Andromeda M31. So this, what you're seeing is the disk of M31, and then those with 3 pointing. You can see one of these is really commissioning that we haven't even have the 10th spectrograph working. So that's why we see that wedge gap there. But with 3 pointing, a total of several hours only, we were able to look at the giant cell stream and seeing these shell-like structures in the kinematic space. So this is really just the one early result coming from DESI, that related stream. And there's a lot of other science from halo to dwarf galaxy and from Milky Way to nearby local universe that we have been doing with DESI. So with that, I would end my talk and take questions. I just want to emphasize the power of these full 60 data set, 60 plus, because there's also metallicity chemistry coming from these surveys in the Northern Hemisphere and in the Southern Hemisphere for the 2 surveys that I've been involved in. And I think the future of all of these with all these big data set will be really brilliant. And I'm happy to take any questions if you have any. Thank you.
Any questions? Go ahead.
So great talk. For the formation of the Milky Way stellar halo, how much do you think it's from the accretion of nearby galaxies that are and then in the early formation of the Milky Way versus stars formed in the Milky Way?
I think that is a good question. There are a lot of reviews on that. If you ask me, I think most of it should be accreted. It's harder to think about, but there are some local, like this. There are recent finding of some of the local halo formation, like in the close to the disk of the Milky Way. But if you talk about like third outer halo, I think most of it should be accreted. But again, that's something people are trying to study, not only about what's the percentage of it being accreted, but accreted by what? By biggest satellites, or small satellites, those kind of things. But yeah, I personally couldn't think about something formed in the disk and then get ejected out. But I think most of it should come from accretion if it's outer halo. But there are recent findings, some of the local halo that come from the formation of the disk, like at early universe, that are kind of more local rather than distant. There are questions online.
I was just wondering, for the streams, the ones you follow up with spectroscopy, how many like contaminants do you find, so stars that do not belong to the stream, and how many do you think you generally miss that should belong to the stream but you're not following up?
Okay, that's a great question. So I didn't give another. So I mentioned about we using AET to follow up the stream in 2018. Actually, we started doing this before that. We did, but I was just 1 or 2 of them I did without forming this new collaboration. And we did one, that time we don't have any Gaia result. So we had to follow 1,000 stars to get 10 member stars to 20 member stars. That was the I have to say 1,000 is more like we're going super deep, but at the end we find that the instrument doesn't even go that deep. So that is another reason. And so that was like pilot survey or pilot program to know what's the capability of the instrument, the AAT, so we know how deep we can go. So we found we were going 2 magnet deeper, that it was not useful. But at that time we are doing 10 member star out of 100 or 1,000 target. And when S5 started, as I said, for a given stream field, we have been doing about 200-ish target per field. And again, the member star depending on the stream. Some of the stream only have several stars. Some of them can go as more as a few dozen. So like some maybe get to 30, 40 stars per field. So and if we do, it depends on how we select them. The biggest constraint actually coming from the Gaia proper motion, right? It depends on how we select it. It's a 1 sigma error, 2 sigma error, or what we are using. So at the end, usually, I would say it varies. Usually, the membership rate is something between 5% to 50% between the stream. In terms of the stars we missed, I think if it's in the field and it's in the magnitude limit, then I don't think we shouldn't miss any unless there's a coincidence. So within several arcs 30 arcsecond, the fiber collision radius, there are 2 member stars. Then we only observe once per field, so we will miss those members, but the chance of those are low. However, I have to say, I mean, let me show you an example, like where is the footprint of our survey? Like, so we know exactly where, so you can see, right? Basically, this tells us what's the field of view of ours. So we basically know where the stream is at. So we look at just that part. This is make this helpful that I'm working together with the discovery team who know exactly where the stream is. You know that a lot of streams have been found and no one really report where they are on the sky other than show a plot. And if you digitize that plot, it doesn't really give you exactly the track. But anyway, we were able to know exactly where the stream is, but a lot of these streams